What's up, everyone? We're here in section 6.7, and we're going to be looking at sinusoidal curve fitting. So basically, we're going to be given a data set and trying to model it with a sine function. The data is known as sinusoidal data when that can be done. All right. So here's our data set. We have the months of a year from months 1 through 12 corresponding to the average monthly temperature for a location. And notice you have a scatter plot of the data over to the right here, and you can see that it definitely looks similar to one period of a sine or cosine function, right? So if the data repeats over multiple years, we can represent it with a sinusoidal function. We're going to do this by hand, and to do so, we need to find the parameters of A, K, B, and H. All right, so let's start with the A value first. We know that A from our equation controls the amplitude of the function, right? Amplitude is the distance from your high or your low points of the curve to the midline. All right, so with that in mind, you can find your A value by simply taking your highest value, so your maximum value, subtracting that by your minimum value. That'll give you the distance from the highest point to the lowest point in the data set, and then divide that by 2 to get your amplitude. Okay, so for this particular data set, the maximum value occurs in the 7th month, and it's 74.2 degrees. Subtract that by your minimum value, which occurs in the 12th month, which is 30 degrees. Divide that by 2. That's going to give you 44.2 divided by 2, which is 22.1. Okay, so if I take my parent function for sine and I bring that into play, it becomes y equals 22.1 times the sine of x. And I have that curve graphed in blue over on the bottom right side of your screen here, as well as the data set that we're trying to model. So notice the blue curves, it's nowhere near representing the data points just yet. Okay. Now we move forward to the k parameter, and we know k affects our vertical translation, right? And that ultimately has an effect on the midline of the curve. You can think of the midline as the average of the high and low points in your data set. So to find k, we simply have to take our highest value, our maximum value, add it with our minimum value, and then divide that by 2. That'll average those two values out. So we're using the same numbers from before, 74.2. This time we're just adding it with 30, dividing it by 2. It's 104.2 divided by 2, which is 52.1. Okay, so now if I take the previous equation that accounted for the amplitude and I bring k value into play as well, the equation becomes y equals 22.1 times the sine of x added with 52.1. Okay, and see the curve is now shifted upward to where my midline is right about here. So it's getting closer to starting to model the points of the data set. Okay, next we find our B value, and B value is our horizontal stretch factor, which ultimately affects the period of your sine function, right? So B, we've always said, is equal to 2 pi divided by the period. Well, in this case, this function would have to have a period of 12, right? Because the data is going to repeat itself every 12 months. So I'm going to say period is 2 pi divided by 12, which simplifies to pi over 6. All right, so bringing that into play, the equation becomes y equals 22.1 times the sine of pi over 6x added with 52.1. And you can now see that the blue curve, it's definitely been horizontally stretched from the previous curve that we saw, and starting to model the width of that data set fairly well. Now, the only thing we have left to do is shift that blue curve horizontally so that it'll get right in line with those points in the data set, okay? So that requires us to find our H value, or our horizontal shift value, okay? Now this is probably the most difficult parameter to wrap your head around as far as how to calculate it, all right? What we're going to do is we're going to take the period of the data set and we're going to divide it into 4 subintervals first, okay? So the period we said was 12 months for this data set. And if we divide that by 4, that gives us a value of 3. So I'm going to create a subinterval from 0 to 3, then from 3 to 6, 6 to 12, or I'm sorry, 6 to 9, and then 6 to 12, or 9 to 12. Okay. And think about what the sine function would look like if all you did was you changed its period to being 12 and you didn't do any other transformations on it, okay? So that equation would be y equals the sine of pi over 6 times x if the period's 12, okay? Now what would that look like graphically? Well, I taught you to plot those 5 critical points, right? And they're all spaced a quarter of the period apart from each other. So the quarter of the period is 3 units. So I'm going to space everything out by 3s here on the x-axis. Okay, and that's exactly what I did when I created those 4 subintervals over to the left-hand side. And this function would begin at the origin. You'd move 3 units to the right, 1 up, then back down to the midline, down, and then back up. So there's 1 cycle of that curve, right? Now, what we want to notice is, where does the highest point of that curve occur? What value of x does it take place at? And that would be right here at an x value of 3. Okay. We'll look at your data set. The x value of 3 corresponds to the month of March, and that's not where the highest temperature of the year takes place at. Instead, the highest temperature is right here in July, in the 7th month. So to find H, we're going to subtract this x value of 3 from the x value of where the maximum occurs in our data set. So H would be 7 minus 3, or 4. Okay, so basically what we're saying, if we go back and we look at this illustration here, is I need my maximum value to, instead of being at an x value of 3, I need it to be over here at 7. So I need this point to shift over to here. That's shifting a total of 4 units to the right, giving me that H value. Okay. All right, so we take the H value into account now, and the equation becomes y equals 22.1 times the sine of pi over 6 multiplied by the quantity x minus 4, and then added with 52.1. That equation has been graphed over to the right in blue there, and notice that it fits that data set quite well now. And you could now use the equation to make predictions about the temperature for this location in future months. All right. Now, one other thing we could do to be a little bit more accurate is we could come up with a sine regression equation using a graphing utility. Okay, this will be more accurate than the one that we've just created by hand. Okay, so You would do this much the same way as how we calculated linear and quadratic regression equations. You put your data set into list 1 and list 2 in the calculator, and then under your calculate menu, you would choose the sign regression option. All right, and if you do that properly, this is what it should lead you to. Understand the parameters here are, some of them are going to look a little different than what we found. That's because this model looks a little different than ours, okay? Um, Notice the argument of sign here is bx plus c. So they are not accounting for the b value being factored out, so that c, it can't be thought of as h now, right? We'd have to take whatever values they give us here, and we'd have to think of it like this, to where the b's been factored out from c, and now the value of c over b, that's going to be somewhat close to the H value that we found by hand, okay? But the A and the values for D should match our values of A and K that we found by hand.